So, any comments on the lab? Has everyone taken a look, at least if not started on it?
Are we required to use R and I?
No, you can make whatever design decisions you find. You can use sockets, RPCs, RMIs, anything else you want. So there is a homework that's also due soon, and then there is a lab. So just make sure you keep up with stuff, and as I mentioned, there is an exam in 2 weeks. Okay, so not the week after, but the week after next, there's an exam on Wednesday. Okay, that will be our midterm exam. So keep that in mind. As I had mentioned, if any of you feel like you want the lab to be due a couple of days after the exam, so you have time to study for the exam, I'm happy to accommodate that. Because the week after that is spring break. So there won't be anything due during spring break. So if you want, I can give it in time. But if you have started, it shouldn't actually take that long to do the lab. Okay, so just let me know what you think. Anyone have anything to say? Comments, lab, exam. Right. So anyway, if you have anything, let me know. I can think about it. So exam in 2 weeks. I'm going to send an email. Wednesday, the week after next, is going to be the exam. The lab and the homeworks are due next week. There was a little bit of work. More of this problem has been created because I had to readjust the schedule because of the storm. But hopefully after spring break we are caught up with the lectures. Exam is out of the way, so we only have labs and homework, so there won't be as much bunching up of things. Okay?
How long is the
Oh, okay, I should mention it. So first of all, exam is not an in-class exam, it's an evening exam. Okay, it's going to be in this room at, I believe either 6:30 or 7. I'm going to check the time. And typically it's a 90-minute test, closed book, closed notes. But because there is no pressure, I usually give extra 15 minutes or so. There's not a problem. So assume an hour and a half. Okay. Final exam is always take-home exam. Okay, and only the midterm, and obviously because if final is take-home, it's open book, open notes. The midterm is in-class evening exam, closed book, closed notes. Okay. I'll send an email later today just announcing the exam for benefit of everyone. Not enough people showed up last time, and I guess today is going to be also lightly attended. And there's an online section. So I'm going to email this, but you have all the details you need to know. Okay, Wednesday of, not the next week, the week after next, 7 p.m. I think it's either 6:30 or 7. I'll verify. I'm sure it's 7. Okay, 90 minutes. All right. Okay, so let's get started here. I'm going to continue the discussion on quality of service and then talk about naming. But before we do that, I'm going to start with the parable because it's Friday and all of you took the trouble to come. So we'll start with the story. So this is about the cow. The story exists in many different forms, but here is what it is. So there is a train with a statistician, economist and a mathematician who are going to some conference on a train, and the train is going through some countryside, and then they see a cow. Then the economist says, look, I see a cow, the cow is black, so all cows in this country are black. And then the mathematician says, hold on, that's not quite what you can say. Based on what we have seen, probably what you can say is, in this country there is at least one cow that is black. And then the mathematician says, that doesn't follow at all. And he says the only thing that I can infer from this is that in this country there is at least one field in which there is at least one cow which has at least one side that is black, which you see. So that's the story. But the moral of the story is you need to be careful about how you interpret data and what the data is. Alright, so we'll continue from that point on. Just to reiterate what we were doing last time, we were talking about audio and video streaming, if you recollect, and we were talking about streaming oriented protocol where you have push based delivery of data, and in that context I mentioned some key differences between audio video streaming and traditional client server request response type application. The main one being audio and video data have timeliness constraints on their delivery. When the server sends some data, it needs to get to the client in a certain amount of time. Otherwise, when the client is playing back the audio and video data, they will see a playback glitch. The video or the audio will freeze because there's no data to show, and that's not a good user experience. And the way typically you specify the needs on what the stream requires from the server, the network, is by specifying what is called a quality of service. These are simply metrics that you specify, like these are the resources I need, or these are this is the service quality I expect for the user to see good performance. That's what it means. And there are many different metrics we talked about: the average bandwidth that you need for the stream to be transmitted, the loss rate that you can sustain, the end-to-end delay that you may want to limit, and so on and so forth. Okay. Now here is a picture that shows you typically what may be done from a quality of service perspective. So here's the server, that's the client, and the server is, in this case, you're playing a stored video file. The file is on disk, you're simply streaming it out to the client. It could be a movie, and the client is simply viewing it. And what is shown here are two boxes which says quality of service control. So the OS at both ends can impose certain restrictions on how the data goes out in order for the stream to see good quality. And that is basically the QoS control. It's also called a policing mechanism. So it's also called traffic policing. So the OS is actually controlling what the application can do. If the application tries to violate something that it said it would do, the OS is going to prevent it from doing it. In this case, with the token bucket example that we are talking about, which I'm going to come back to, what a token bucket is doing is it's simply limiting or policing the rate at which the data is getting sent out. If you try to send at a rate higher than what you said you would transmit, the OS will delay some packets and prevent you from exceeding your specified bandwidth rate. Okay, so if you say this stream is going at 100 packets per second, if you suddenly start transmitting 120 packets, your OS is going to hold some packets that only let you transmit at no more than 100 packets per second. So that's called policing. That's how you can control what your application does, and it doesn't just start blasting packets and saturate the network or some such thing. Okay. So there are of course mechanisms you can have inside the network in the routers that also provide quality of service guarantees. But as I was talking about last time, this requires you to have protocols in the routers that will enforce such mechanisms. They are expensive to implement. And as a result, the internet philosophy is keep the network simple. Internet is a best effort network. It does not provide you a real quality of service guarantee. When you send a packet, there's no guarantee on whether it will be delivered. It could be dropped. It may take arbitrary amounts of delay for it to go from the client to the server. So about the only thing you can do in the today's networks are to implement QoS at the edges, which are really at the server and the client of the edge routers to prevent the application from misbehaving or into whatever it's saying. Okay. So that's the picture to keep in mind. We're going to come back and talk about token bucket again. Go back one slide here. So that was a picture I showed you about a token bucket, and this was at the very end of the class. I'm not sure this was very clear, so I'm going to redraw whatever I said. So a token bucket is a way to specify some service quality on the stream, where you specify two parameters: a rate, okay, the average rate, and a burst. Okay, the average rate says that the application is going to transmit at an average rate of R packets per second. The BERT says that every once in a while, the application is allowed to exceed its rate R, and you can send a burst of B packets all at once instantaneously. If you send a burst of B packets, you may temporarily exceed your steady rate of R. So you're allowed to exceed that rate every once in a while, but there's a limit on how you can exceed it, and that is specified by the burst rate R, B. Okay. Now you can specify this in many different ways. So for instance, if you set B to 1, okay, which means that there is no burst, you can only send one packet at a time, and you specify R. So R comma 1 essentially says you can only transmit at a constant rate of R packets per second. You're not allowed to essentially exceed it at all. Okay? But you can have arbitrary burst sizes, which says if I have set B to 100, which says I can send at R packets per second, but every once in a while I can send a burst of 100 packets, up to 100 packets, which may cause that rate to be exceeded. But that's the that is the limit on how much I can exceed, right? How much my instantaneous rate can exceed the average rate. Okay, so this allows you to control the rate at which you send data into the network. Now another way to actually look at this is, if you actually look graph, let's say time and the x-axis and data sent on the y-axis, and let's say the data is fluctuating in the graph, how you send data over time, and keep fluctuating, what a token rate parameter actually does is it sort of limits you to this curve that I just drew, which is essentially R times T plus B. So the slope of the curve is R, okay, and the intercept is B. Okay. So what that says is at any time T, you will basically be bounded by this curve. The amount of data you send cannot actually be above this line. It always has to be below this line. Okay. So another way to put this is between any time T1 and T2, the maximum amount of data that you would have sent will be limited by this quantity. R times the difference, that's the time, which is same as R times delta T plus B. Okay, that's basically that curve. So that is somehow limiting what you can do. So at any point you can send up to B packets, that's the intercept here. Okay, and then you have a limited steady rate. Okay, so very simple mathematical explanation of what a token bucket regulator, it's also called a leaky bucket regulator. Okay? Now the example here shows you how it is actually implemented. Okay, you specify these two parameters, then your network card will start generating tokens for the stream at a rate of 1 token every 1 over R seconds. Okay? So if say R is 10, that means every 10th of a second a token is generated. Okay? And it's going to be kept in this most abstract concept of a bucket, which has a depth of B. That means that the bucket can hold up to B tokens, but no more. If you have more than B tokens that have accumulated, then any new token that is generated is thrown away. So you can at most have an excess of B tokens at any point. So whenever the application is sending a packet, what you will have to do is look at this amount of tokens that you have generated, pick a token, and only then are you allowed to be sent out. If the bucket is empty, that means there are no outstanding tokens. You have to wait for the next token to be regenerated before a packet can be actually sent out. Okay, is that clear? So that's basically the mechanism that you can use. So essentially, because you're generating tokens every 1 over R, the average number of packets you can send is going to be bounded by rate R. Every packet needs a corresponding token before the OS will actually transmit. Otherwise, it will be held back until a token is generated. Okay? So this mechanism is referred to as a leaky bucket or a token bucket regulator. It's a simple rate regulator that controls the rate at which you send data. Is that clear? So now we'll talk about a few other mechanisms. The first mechanism is buffering at the client, which is a very straightforward idea, but I'm going to explain why you need it and how that actually can help you get better video quality when you play back some video. Okay? So this is again timeline. Okay, there are 3 different scenarios here. So the top line here shows you how the packets are being sent by the server. Okay, so this is packet 1 was sent at this time, packet 2 at this time, 3, 4, all the way till 8. Okay. And we are going to assume packets are going over the internet. Okay. So what that also means is the delay that a packet is going to see by the time it gets to its destination is going to be variable, because the internet doesn't make you any guarantees that when you send a packet it's going to reach the destination in a certain amount of time. That time is variable. Okay? So as a result of this, this is when the packets are actually received at the client. Okay? So packet 1 was received at time t equal 1 second. Okay? Packet 2 saw a larger delay. You see 2 was sent here, but it saw a larger delay and it only reached at this point in time. So the delay that it saw is larger than packet 1. And same with packet 3 saw a larger delay, and then after 3, 4, 5, 6 seem to come right after 3 is received, and then there's a gap. 7 takes a longer time and 8 takes a longer time. So this is how the client has received the packets. Okay? Even though the server is sending them at a steady rate, let's say at 30 frames a second or 30 whatever packets or images a second, you are receiving them in this order, because the packets are seeing variable delay in the network. Now this is what the client is seeing. Our goal is to ensure that when you are playing the video out, the user is not going to see glitches, meaning that there's always data to be played out that has arrived over the network, so then I can keep playing in a smooth fashion. Okay? So one way to do this is to do what is called buffering. Okay? What buffering says is that you do not start playing the video as soon as the first packet is received by the client. You are going to put them in a buffer, accumulate some data in the buffer, and then start playing it out. And so then if there's always some data in the buffer, you can always continue to play. If the buffer runs out, then you're basically going to have a playback glitch. So in this case, the client has decided to accumulate a buffer of 6 packets before it starts playing the video. Yeah, so even though the first packet is received here, it waits for 5 more packets to be received, and then it starts playing the video. Okay, so until here, after you hit play, it's going to say waiting, and then wait for 6 packets to be received, then it starts playing them. Okay. Now once you start playing them out, you're going to play them out at the same rate at which you are sending them. Because if it's 30 frames per second, you have to start playing 30 frames per second. Okay. So you are going to start playing them out at a steady manner. Okay. And data is continuing to arrive. Okay. So you'll see you played 1, 2, 3, 4. At this point, your buffer is down to 2 packets because you started with 6, and that is when the 7th packet arrives. Okay. So now you have 3 packets. So you are playing 6, 7, and now it's time to play 8, but 8 hasn't arrived yet. 8 hasn't arrived. So your buffer is empty at this point in time. So you will see a playback glitch. Okay. So in this case, you will basically, your video playback will freeze. You will wait for more data to arrive, and maybe you will wait for the buffer you won't start playing 8 as soon as it comes. You may wait for some more packets to arrive, refill the buffer, and then play it out. So the idea is the larger this buffer, the lesser are the chances you are going to run out of data. Okay. In this case, you decided to choose 6 packets in your buffer. So your buffering was 6 packets or 6 frames. If you had chosen 10, then maybe you wouldn't have seen this problem. Okay, maybe you have more data, so the probability of a buffer underrun has reduced as a result of this. Okay. So it's up to the client to decide how much you want to buffer before you start playing it out. So the thing to keep in mind is the more you buffer, the longer the delay before you start playing the video. So from a user perspective, user has hit play and they're simply waiting, and your wheel is spinning saying waiting for data, and then you're just having the buffer build up. And if you wait too long, the user is going to say something is wrong, the video is not playing, and give up. Okay. If it's too short, you have very little data in the buffer, and you will likely see buffer underrun if you see variable delays in the network. Okay. So you have to balance this trade-off. You don't want the buffer to be too small and have buffer underruns, or if you make it too large, you make the user wait for a long time to start the initial playback. Okay, that may not be satisfactory to the user either. Okay, so you have to balance these 2 constraints. Okay, but if you do this, what you have done as a result of just having a very small memory buffer at the client is you have gotten rid of the issues created by variable end-to-end delays. This is referred to as jitter. By different packets see different delays. If all packets saw the same delay, you wouldn't see this. They would arrive at the same steady rate, just offset from the client, from the server. Okay. But because the delays are varying, you'll see that the gap between packets at the client is going to keep fluctuating. Okay. So that is referred to as jitter. So because of jitter, you can see buffer underruns. And you can use very simple buffering, no additional mechanism, you just have maybe. Okay. So this is one issue that could arise, and this is how you solve it. Another one is packets may get lost in the network, and then what do you do about that? Okay. Now if you say I am going to simply retransmit in typical client server applications, the packet losses, you just have TCP retransmit that data, eventually it is received at the other end and everything is fine. Okay. Now in this case you may have problems with that approach, because if you retransmit, it's going to take even longer for that lost packet to be received, and you may have already reached the point where that packet needs to be played out and you see a glitch. Okay. So late packets are as good as not receiving any packets in this case. So there is no, in some sense, there is no point in retransmitting lost packets, because it simply makes a missing packet even more late and causes more problems. Okay. So there are many ways around this issue. Either you have very large buffers so that there is still trying to retransmit, that's one approach, a straightforward approach. Okay. Another approach is you can add redundant images or data to your stream and reconstruct lost data at the other end. Instead of retransmitting, you have redundancy in the data you are sending. So you take the data that's already been received and you can use the redundant part of that data to reconstruct missing data. This is called forward error correction, something that I haven't actually talked about, but something you may want to keep in mind. You are simply using redundancy. When we talk about fault tolerance, we will see various ways to add redundancies to the system to deal with failures. Packet loss is an example of a simple failure from a network's perspective. It failed to deliver the packet. Okay. You can deal with it by retransmitting, or you can deal with it by adding redundant data to your stream, so that I can use that extra data to reconstruct the missing data. When we do fault tolerance, we'll come back to this, but at the moment we won't talk about forward error correction. Instead, I'm going to show you some other very straightforward techniques that don't do any error recovery, but they mitigate the impact of a loss. Okay, so here is the example. Here again, there are two scenarios here. So this is the top scenario, just shows you how data was sent. It's 1, 2, 3, 4, 5, 6, 7, 8. So you're just sending data in order. Okay. And in this case, let's say this is an audio stream. So each packet can contain multiple audio samples. Okay. Typically, if it was video, your video image is large. You can't stuff an entire image in one packet. In fact, an image will be split into multiple packets. But I'm talking about in this case, just to make an example simpler, an audio stream where the samples are small. Okay. There may be a few bytes, so you can stuff multiple of them in a single packet. So you send the first packet with just 4 samples, and another 4, and another 4, and that gray one got lost. Okay, meaning that it was never delivered. Now if you're playing this audio, what will happen is after you played out the 8th packet, you're going to have a gap of 4. This is going to be a glitch. Okay, so if it was audio, you will see a silence, and then the audio stream will resume, but there will be some gap. Okay, you may miss a word that was spoken. When somebody is saying something, they're missing data, that word is lost, you then start from the next word. Okay, something like this is going to happen in this case. Now that is a problematic thing because you just lost some data. Okay. So what could you do to mitigate the impact of a loss? So as I said, you could have retransmitted that packet, okay, but that may arrive too late and you already seen the glitch. Okay, so here you're just skipping over missed data, you're not trying to get the data and play from where you left off. Here is another way to send that data. So what you are going to do instead is scramble the data in the order, or scramble the order in which you send data. Okay, instead of sending packets in order, you are going to take the first sample of the first packet, first sample of the second packet, 5, 9, and 13. Put that into the first actual packet you send. Okay. Then you take sample 2, 6, 10, 14. Those are the second of each of those, and put them in the second. And this is the third, and that's the fourth. Okay, so now what you have to do is you have to wait for, you can't play them in this order. This won't make any sense. Just because you scramble the order of send, you still have to play them in order 1, 2, 3, 4. Okay, so you will basically wait for all of this to be received and take this, 1, 2, 3, 4 and play them in that order. But because you lost the same packet, what has happened is the losses are now spread across a larger part of your audio or video stream. So that means that it is much less likely you will actually see the impact of this kind of loss than a concentrated loss. Okay, maybe when you're speaking a word which has multiple samples, one of the samples is lost, but you can still make out what somebody said. You may just feel a little jarred. Or if you're playing a video, if you instead of 30 frames a second, if you see 29 frames in 1 second, it's hardly going to be perceptible to the eye. Yeah, because that's, but if you lose maybe half a second, you will actually see a glitch. Your eye can perceive that there is a problem. Okay. So, but if you scramble it in this fashion, you still lost 4 packets out of 16, but you spread the losses. Okay. And this will actually make it less perceptible to the human eye or less perceptible to your ears. And there's a loss. We are deciding that we won't retransmit. We're simply going to play it as it comes in, but now we're trying to mitigate the quality. Okay, your question? Any other questions here? Okay. So I'm going to show you essentially what is the state of the art in audio and video streaming today. Okay. So first of all, I should mention a few things. Okay. When audio and video streaming protocols were designed, everybody decided that UDP is the better way to send that data or other than using TCP. Okay. And the reason was TCP inherently has a notion of error recovery and retransmissions. Okay. TCP will say, this packet has not been received, I didn't get an ACK, so I'm going to retransmit it. As we just discussed, retransmissions may not help in this case. It's already the time for playing that packet went by. So if I receive a packet after I've gone beyond that point in the audio and video stream is useless too. Okay, so they decided UDP is the way to go. UDP has no retransmission, so it just keeps sending its best effort. If data is missed, you can use one of these other techniques to address that issue. Okay? So by and large, all the protocols that were designed in the first 10-15 years in the research community were UDP based streaming protocols. Okay? There are many protocols, many got deployed, but what happened was over time, because the web became so popular, okay, people started simply watching video clips or audio clips in a browser, okay, which also meant that the data was coming to you over HTTP. So that's how you get any data in a browser. HTTP, remember, runs over TCP. Yeah, HTTP doesn't run over UDP, it simply runs over TCP. Okay? So even though UDP is inherently better suited for streaming, and even though all the early streaming protocols, there are a whole lot of them, there are things like Real Player and Microsoft Windows Media Player, which still exists, but in those days they all used their versions of streaming protocols that were UDP driven. Okay? None of them actually took sort of shape in the marketplace. What eventually succeeded by simply the fact that web became popular and people started watching videos in browsers was HTTP based streaming. You simply send a HTTP request and then wait for the data and start playing. Okay? So even though TCP is less than optimal for streaming, it is by large the way streaming actually takes place. Okay? So efficiency wise is not the right approach, but that's how most of the videos deliver. And that's simply because of a convenience. And you know how to do browsers. If you just embed a video or audio stream, it just gets delivered over HTTP. Okay? So this is basically the thing to keep in mind. Okay? So what that also means is because retransmissions cannot be turned off in TCP, you will be stuck with them. You may need a slightly larger buffer because if there's a missing data, you can't skip and go over it. TCP won't even deliver it. It will wait for the retransmissions to take place. So you may actually from an application standpoint see even more jitter because the data is being retransmitted, so it may look like it's taking even longer for the packet to show up. It's actually the second attempt that the packet is sent, which is why you see longer delay. So buffering may have to deal with some of the artifacts of more jitter and so on that you see. Okay? So that's the first thing to keep in mind. Okay? So real world HTTP streaming is the way most of the videos delivered over the internet. Whether you do YouTube, whether you do Hulu, whatever streaming services you've seen, they are by and large all running over HTTP. Okay, HTTP runs over TCP. Now, having said that, you still need the ability to deliver video at different quality to your users depending on which device they are viewing the video from, what kind of bandwidth they have. So for instance, if you have a cell phone that you're using to view a video, you have a small screen. Right? If you're watching the same video clip on a desktop, you have a much larger screen. If you use the same resolution to deliver video to these two devices, the user experience will not be the same. Because if you say I use the lowest common denominator, which is my small mobile phone screen to encode the video, because that is how much that screen can accommodate, then when you see it on a much higher resolution, bigger display, the video quality will look terrible, because you encoded it for a small screen. And vice versa, if you do it for a larger screen and you deliver it to a phone, you may take much more bandwidth than the phone actually can accommodate, and maybe the phone doesn't even have that bandwidth. You are maybe watching it over a cellular connection, but the connection may be slower than if you are on a gigabit Ethernet. Okay? So the bandwidths can vary, the screen sizes can vary. Okay? So you need an ability to deal with users' requirements in order to give them the best quality for the resources they have, which is the screen size and the bandwidth they are connected. The way this is actually dealt with is very straightforward. Every video is encoded at multiple bit rates. You have a low quality version of the video, a medium quality version of the video, high quality version of the video. So the server actually stores multiple files, each of which has the same video encoded at different quality levels. Quality is the resolution or the bandwidth. You can have 128 kilobits per second, 256 kbps, 1 megabit video, you can even have more than 1 meg. You are watching HD, it will be more than a megabit. Okay. So the server will just keep all of these resolutions. Okay. And on the fly, you have to detect what quality the user can actually sustain, and then pick the right quality level and deliver it to the user. So two users watching the same clip from two different devices will actually see two different files, which are two different resolutions of the same video. Is that clear? And the server needs to figure out what is the right quality to set. It's not going to magically know what quality to deliver. It can make some guesses based on when you make a request. The request includes what kind of OS platform and what kind of browser it is. So if you see something like Android or iOS, there's okay, that's a mobile device. Or if you see Windows or it says Linux, you may think that that's a desktop class device. So you may be able to make some educated guesses about what kind of machine the user is coming from. You will often not know what bandwidth the user is connected on. Okay, you may be on a shared Wi-Fi network in a coffee shop where everybody is watching some clip. Okay, or you may be sitting at home where you have the full bandwidth of your broadband connection, or at work where you have gigabit. So that a server won't know. Okay? Server has to figure this out on the fly. Okay, the way it is done is there's a version of streaming protocol that's used, which is called Direct Adaptive Streaming over HTTP. The acronym is actually called DASH streaming, which is essentially Direct Adaptive Streaming over HTTP. What DASH streaming does is very straightforward. It doesn't try to make any guesses at all. Okay? It will dynamically figure out what is the quality level to send. Okay, so here is how it works. So this is time. Okay, so let's say you have a large video clip. You chop it up into smaller pieces. So then this is the first 30 seconds of the video, next 30 seconds, next 30 seconds, and so on. And then you have them at different quality levels. You have the red, the green, which is the low quality version, the red is the medium quality, blue is the high quality version. Okay? So 3 quality levels, and then you taken a large video file, you chopped it up into smaller pieces. Okay? So when the client starts up, you may start with somewhere in the middle. I don't know what the client is. I'm going to start them at the medium level. So you send the first, this red chunk is sent over. And then you observe what happened. Okay, you make the client, the browser, send back a small report saying, did you receive all the data? Were there playback glitches? Were there errors? Okay. If you see that there are problems that the user saw when they played this one, you will for the next 30 seconds, you'll drop their quality. You'll dynamically send them the green chunk. Okay, the second chunk will be green. Okay. On the other hand, if the user reports saying everything looks good, there was absolutely no problem, error, video came out beautifully, you may say, okay, maybe the user has more network bandwidth resources and you can actually increase their quality and go to the blue level. Okay. So you will keep varying the quality level on the fly. each time after each chunk the user's browser will send a report saying what was the quality observed, were there glitches, were there errors, okay, were there other problems, and depending on that the server will make a decision at each point saying should I bump up the quality or bump them down. So you may actually see this happening. If you're watching a YouTube video, suddenly your video may start looking grainy, especially if you had a playback glitch. You'll see that the next 30 seconds may become grainy. If the network starts behaving better, the quality will get better. What is actually happening is this: in the background, the server is dropping your quality level because you're seeing it cannot push enough data to you. You don't seem to have the bandwidth. So it will drop the quality. So it can try to push less data on the network than you. So this kind of techniques are referred to as dash streaming. This is how many HTTP servers actually try to control the quality that users see. Any questions here? Yes. Okay, so what is the quality? The quality, first thing that the quality means is the resolution, meaning how sharp the picture is and so on. Right? So if you have a low bitrate video and you see it on a larger screen, the video will look grainy. It may play out well. So that's the first metric of quality, is the resolution. Other metrics may include, are there glitches? That's the experience. Okay, if there are more glitches, that means that you are not seeing. So the quality is like what we talked about in quality of service. There are many dimensions. There's the resolution, there's the errors. You may be seeing playback errors, meaning packets are not getting through, they're coming late, they are getting dropped. Then you may also see the bandwidth, resolution, jitter, packet loss. So all of these will constitute quality that you see. Okay, you can report all of those metrics, and based on that you can see what is going on. Can vary the quality. Any questions on this? So I'm going to quickly talk about multicasting, stream synchronization and multicasting, and then we will move on to the next topic. Okay. So stream synchronization is yet another issue that arises in audio and video streaming. Okay. So in this case, what happens is when you start playing, let's say a movie, okay, there are actually not one but multiple streams coming to you. There's at least a video stream and an audio stream. The video stream is the images that you see. The audio stream is whatever you see on this here on the speakers. Okay? And when both are being played out, they need to be synchronized. Okay? Meaning when you see an image in the video, you need to hear the audio sample that corresponds to that image. Okay? If you are slightly off, you will see that your audio is not lip synced to the video. Okay? You will see that the characters are speaking something, but what you are hearing is not lip synced to them. You are hearing some different words that don't seem to correspond to what they are speaking. There is a slight offset. Okay? This is when you lose synchrony, because your audio and video is not synchronized. I have a picture here that shows you. So here is an audio stream and a video stream. They are coming in to you, and then the audio stream is sent to the speakers, the video stream is showed on the screen. Okay? And since they are being sent by the OS to two different devices through two different device drivers, there needs to be some coordination on when you play something on the screen, whatever you are hearing on the speakers has to be the same corresponding data. Otherwise you will see bad quality. Okay? This has nothing to do with what was sent, it's just how you synchronize the play out of the application. And you may have stereo quality audio, which means that the audio has to be played out through multiple speakers. Okay, those also have to be synchronized. Now, so what this also says is, in addition to transmitting and buffering and all of this, since the audio stream actually have multiple sub streams, one for the images and one for the audio and other things, you need additional mechanisms called synchronization. Okay, so here basically you need clock synchronization. The way this typically would work is every audio sample is going to be timestamped. Every image is also going to be timestamped. Okay? So what you need to simply ensure is when you play something on the screen, you look at that timestamp and you will basically play the corresponding timestamp audio sample on the speaker, and you will be good. Okay? Keep in mind that the rate are not the same. Okay, so it's not like there's one audio sample for every one video sample. audio is being captured maybe at 44 kilohertz per second, that's a second. Okay, video may be 30 frames a second, that's only 30 images per second. So you still have to keep track of not the exact match, but the closest match, so that you keep track of varying rates and so on. But nevertheless, you need to perform the synchronization. Okay? So what that also means is when you are capturing the data, okay, again the data is going to be captured by a camera and a microphone. Okay? You need to timestamp the data and ensure that the data is synchronized when you capture it, so that these timestamps are present when you play them. Okay, so all of these are additional things you will have to implement. That adds overhead in terms of ensuring there's a common clock that you use to assign timestamps and so on. And when you play them out, there has to be some coordination. The player has to perform this coordination. So if you do all of this, you will actually then see reasonable quality. That you have way to deal with packets, losses, way to deal with jitter, way to handle varying resolution, way to handle varying network conditions, because not like bandwidth you see from the network is going to remain the same. It can fluctuate, it depends on the congestion in the network. So you have to adapt dynamically and you have to synchronize this. So if you put all of that together, you have a audio and video streaming system. Okay? So all of those things have to be dealt with. Any questions on synchronization? So I'm going to quickly mention multicasting. We're not going to spend too much time on this. We will come back to this later, hopefully if you have some time. So what multicasting is simply a way to do one-to-many or group communication. Okay, you do one send and there are multiple recipients. Okay, typically when communication is one-to-one. When you send some packet, it's received by some unique sender that you identify. In multicasting, you send it once and it's received by a group, all of whom are listening for this packet. Okay, this is especially important in audio and video streaming because increasingly there are live telecasts over the internet. Okay, you can tap into a stream of some sporting event. Okay, and that same data is being delivered to hundreds, thousands, in some cases millions of users. Okay. The server is not going to sit and do a million sends for every packet that needs to be sent out. Okay, that will simply increase the overhead on the server. Okay, think about if you're let's say you're doing Super Bowl, which is watched by millions of users live over internet streaming. You can't simply do multiple unicast sends. Okay, that's simply going to increase the overhead because every packet you will have to execute the send command that many times. If you have to send the data individually, you would rather just send it once and have the network delivery. This is often achieved through what is called multicast. Multicast can be implemented at the IP level, okay, which means the router has to support it, or it can be implemented in the application level. I'm going to show a picture of application level multicast where these square boxes are network routers. The circles are actually machines or intermediaries that are deployed in the network. Okay, so here is your I think the server is, in this case, is D, okay, or rather C, excuse me. Server is C and the end host is A. So the server just sends it once, it reaches D. D may send it to multiple entities, okay, and then each of those entities will keep forwarding it, and at the leaves you will essentially have your recipient. So you basically have a distribution tree. Okay, so basically think of it as a tree. Okay, so this is your server. It does a single send. Then the application level multicast middleware is going to send that back, 2 copies of it to 2 nodes. These 2 nodes are going to forward copies to their children and so on. And all the end users are leaves of this tree. Okay, so by doing one send, you have multiple recipients who will eventually all get the data. Okay. So this is referred to as multicasting. Okay. Typically, this is now done today using what is called an overlay network, which is simply a layer of application nodes that are doing the forwarding. Just as when we were talking about message queuing system, we had MQ routers, which are different from the network routers. They're simply application level entities that were doing forwarding. Here you also have application level entities that are forwarding your data to other intermediaries until they get to their destination. Okay. We will come back to some of this when we talk about content distribution networks, because they are also overlay networks. Okay, they are used to perform some of this distribution. Okay, so we'll stop with this topic here. We're going to switch gears and talk about naming for the remainder of this class. Okay, so this is a new chapter in the book. Okay, I think we are done with the chapter on communication. We are going to now look at the next chapter. This one is going to be brief. Communication chapter took us about 3 or so lectures. Naming we'll probably go through quickly and then move on to some other topics in the course. Okay. So first I'll talk about what is this problem of naming. Then I'm going to talk about this whole issue of name resolution. And I'm going to use an example to illustrate all of this, which is the example we'll use. There are two. We'll use the example of DNS, domain name system, as a naming system, and we'll talk about directory services. Okay, I've also often mentioned directory service. Okay, when we talked about RPCs and so on, we'll see some examples of how directory services are implemented in distributed systems. Okay. So, what is the problem of naming? Okay, so let's talk about that first. So, essentially, the problem is as follows. When you have any system, whether it's centralized or distributed, you have resources in your system. Resources could be any abstract quantity. It could be the process, it could be the files, data that they access. And the way typically applications or users access these resources is by giving the resource a name. Okay? Each resource is given a name. Okay? You address the resource or you access the resource by specifying the name. Okay? And so that is essentially the problem of naming. Okay, how do you specify names to objects, and how do you, when a name is specified, figure out what object has that name and get to that object? This is the problem of naming. And now we'll see why this is more unique. So this has nothing to do with distributed system itself. Every system that you think about, computing system has a name. Servers have names. Files have names. Okay, so all computing entities will have names, whether they are centralized or distributed. Our goal actually in this lecture is going to be, once you understand what naming is, to see how we build very large scale naming systems. Because distributed systems can be large. They can be global in scope. Okay? Their naming service has to be able to scale to address such a large system. So we will see how to design naming systems that are tailored for very large distributed systems. So in this context, what we will see is the naming system itself is going to become distributed, because it's addressing such a large need. You can't run the entire naming server on a single machine. So the naming system itself becomes distributed, which gives us the problem of how do you design a distributed naming system, not a centralized one. So that's really what we are going to go after. But I'm going to start slow. I'm going to explain naming, what naming is, what name resolution is, using some familiar examples from file systems. And then we will go and look at some real naming systems, and using DNS as an example. So this picture is going to show you two canonical approaches to implementing any naming system. Okay. There's going to be a peer-to-peer hash-based approach or a hierarchical tree-based approach. In both of these cases, okay, forgetting the picture, what's happening is the user or the application has come with a name. Okay. The naming system is going to map it onto the object. So here is what this name corresponds to. Okay. In RPC's naming, we basically said, I want this server, then the naming system said it's running on this machine with this port. That was the mapping we performed. Okay. Whatever it is, the naming system is performing a mapping. You come with the name, it maps it onto some object. Okay. So if you remember when we did peer-to-peer system, I said these are key value stores. You specify a key, okay, and then you go and find the value. Okay. So you can use that idea to implement naming, because in this case the names are keys and the values are the objects that they map. Okay. So that is how you may use a peer-to-peer or a hash table approach to implement naming. Having said that, we are not going to look at this kind of naming systems at all. Instead, we'll spend all of our time on these kinds of naming systems that are hierarchical in nature. Yeah, but keep in mind there are two approaches, and we are not going to really discuss one approach because the principles are the same. So I'm just going to use this one just to keep the discussion simple. Okay? So in a hierarchical approach, we'll see that there is some hierarchy of names, and we'll see how the naming system works and so on. But that's what we're going to do. But the end goal is the same. You basically send a request saying, here is a name, resolve it for me. Name resolution says map it to whatever it is associated with. So we'll start simple and we'll see how to do this in file system, because that is probably the simplest example. Okay. So the way naming works in file system, every file has a name. Files are organized hierarchically. There are directories or folders, you can put files in them, folders may be part of other folders and so on. And what you will have is a hierarchy of this sort, where you have a root directory at the top, there are some subdirectories and so on and so forth, and the leaves of this hierarchy are all files in your system. Okay. So now if you have any application, let's say it's an editor, you open Microsoft Word or some such thing and say, specify a file name, saying I want to open this file. What Word is going to do is go and present this file to the file system, saying user wants to open this file. Now tell me which file it is. So then the file system has to figure out, if you said it is, in this case, you have a mail client that says it wants to open this file, it use a name, that's the file name. Okay, it has to then, the file system has to go and figure out what file corresponds to that name, and then let the application access that file, data from that file. Okay, that process is referred to as name resolution. Now, the way it actually works in a file system is, you are going to perform a hierarchical lookup. Name resolution involves a lookup. Okay, so if you want to resolve this name, /home/team/mbox, which is the mailbox for this user whose home directory is here, you are going to start at the top, which is the root directory. Okay, so you start at the root directory and say, is there a directory called home in root? Okay, so you will basically open the root directory and look for a directory called home, and you will find that directory, so you will come to that node here. And then you will try to do the next level of name resolution, which is there another directory called Steam inside this home directory? Okay, so you look at all the subdirectories there and look for one called Steam. Okay, if you find it, you will go down into that subdirectory and do the next level. Okay, this is the last level of resolution, so you are going to ask, is there a file called mbox that is present in that directory called Steam? You look at all the files, you find the name called mbox, you'll say, okay, that's the file. So this, eventually you'll sort of traverse through this hierarchy and land up at that file. Okay, so that is name, this is how a file system will take a name and map it onto file. It will start at the root directory and it will descend down the hierarchy, resolving the name one component at a time until it reaches the leaf and it finds the object, or it may not find the object, in which case you will say there is no such file. Okay, is that clear? So now keep in mind that often when you open files, you will not specify the full name. That's the full name of a file. You may simply say open a file called project1.java. Now what happens internally is, although you have specified only the last part of the name, okay, the OS is going to actually take that and construct a full name. Okay. It will look at the current directory and add the prefix of that directory and construct the full name and hand it to the OS file system for resolution. Okay, so even though users may not specify the entire name every time you access any file, internally your system is still doing this for you. That's the thing to keep in mind. Any questions here? Okay, so now I'm going to talk about distributed file system example and how you do name resolution. Okay, just to give you the first flavor of how name resolution works in a distributed system. So in this case, what you have essentially done is you have the same file that we showed here. Okay. But essentially there's a network mapping. You constructed a network volume that you're accessing those files from another machine. This is done using any network file system. It doesn't matter which one. In Unix you can use NFS. In Windows you can create a network drive. Okay. On a Mac you can create a network volume. Let's assume that has been already created. Okay. So what that allows you to do is, on the second machine, you can access files that are stored on the first machine. Okay. So when you have a network drive, that's what's happening. If you have an E drive or whatever on Windows, the files are on a file server somewhere. Okay. So now the question is, if you try to open a file here, and the file is actually on a network share or a network drive, how does name resolution work? Okay. So it's going to work the same way. You are going to start at the top You're going to start resolving the name. At some point, you may hit a point which is, that's a network mount point. Any files that are in this drive or in this folder are actually on a different machine altogether. Okay. So you'll forward the name resolution request saying, I resolved the name to this point. Okay, now you go and do the rest. Okay, so in this case, you'll basically come here and then essentially send that request off to the server saying, you go resolve the rest of the name. Okay, and then the server will take the name that is given to it and map it to a file. Okay. So what this is showing you is a very simple example where the name resolution process is now distributed. It's no longer centralized. In the previous case, the entire name resolution happened on one machine. In this case, name resolution is split across multiple machines. Part of the name resolution happens on one machine, and then the remaining of the name resolution is actually happening on the second machine. So the processing is split. And you don't need just two, you can have arbitrary levels. Okay. So this is the principle we are going to use. This is distributed naming, where you cannot, your name resolution spans multiple machines. In order to get to the object you want, the processing of that name is handled by multiple entities until you figure out who actually has what. So the naming system has become distributed. Is that clear? So now we'll talk about, with that background, talk about a real naming system. This is going to be, we're going to use the internet. That's the largest naming system you will find, okay, one of the largest at least, and use that as an example to see how to construct a large naming system. Right? There's lots of entities that are involved in resolving names. Okay? The example we will use is the DNS or the domain name system. Okay? If you've heard about DNS, you know what I'm talking about. If not, here is what it does. So if you give any machine name, it resolves DNS, just maps it to an IP address. Practically any time you specify any machine name, let's say it's a browser, you say www.umass.edu, that's what you specify to your browser. Your browser has to perform a name resolution or send it to the OS to perform name resolution saying what is the IP address of this machine. Because the way you are going to send a request, set up your HTTP or TCP connection is to an IP address. So the first step of that connection setup is to map this name to an IP address. That is going to happen through the system called DNS. Anytime you want to do this resolution of machine names to IP addresses, you send it off to DNS. DNS will do the name resolution, come back to you with an answer saying this is the IP address. Okay, so we'll see how DNS works as an example of a large distributed naming system. So we are going to learn concept just by looking at an example. Okay, the first thing in any large distributed naming system is there are going to be hierarchical layers. Each layer is responsible for a certain part of the naming hierarchy. Okay, so typically you will see a global layer, an administrative layer, and a managerial layer. Okay, and I'm going to show you a picture of how this maps into the DNS. So this is an example of the internet naming system, okay, domain name system. Okay, so you will see the top level domains, there's a root there. The top level is all top level domains. This is .com. Okay, this server is responsible for anything that ends in .com. Okay, any domain that has a suffix that ends in .com will be responsibility of this server. The .edu. Yeah, any all educational institution names fall under this server. Okay. .gov, and there are country level naming system. That's .us and .nl and .in and each country is also given a suffix, and all the machines that belong to that country's systems will be in that domain. So you will have a whole bunch of these top level domains. But you must have heard or seen all of this. Yeah, .com, .org, .net. So they are all top level domains. That is the global layer in DNS. Okay. The next level is administrative layer. So this is where actual organization servers are. Okay, so you will have sun.com. Okay, so you will have IBM.com. So this is the server that belongs to that company that is responsible for naming all the machines within that company. Okay, so you will have within edu, you will have umass.edu. There is a UMass DNS server that is going to answer requests for all machines in the UMass domain. Okay. And so you will have similar organizations that fall under each of those top level domains, and there will be millions of them in certain cases. Okay, so you only show lots of domains in it. And then you will have a hierarchy. Within that there may be sub-organization. Okay, within UMass you have cs.umass.edu, or you have ecs.umass.edu. Those are subdomains, and each of those subdomains may have their own servers. Is that clear? And then at the very bottom you will actually have machines. Okay, so you may have within umass.edu you may have a machine called www. That's the web server. You may have ftp.cs.umass.edu. You may have mail.cs.umass.edu, which is the mail server. So they will all be leaves. So the leaves here are machines. Okay, everything above this is a hierarchy of domains. Okay, the top level domains, organizations, sub-organizations, and then you have sub-organizations, and you may have machines. Okay. So this is representative, although this may be somewhat obvious if you know anything about DNS. This is representative of any large-scale distributed naming system. Okay. Each entity that is shown here is going to perform name resolution for the subtree that's under it. That's how it's going to be hierarchical. Okay, if you want to resolve any name that ends in .com, you'll start at the root and then you'll end up here. And then you figure out where is IBM.com or www. You'll start here and then you'll start a descent. Exactly what you did in the file system case. You'll keep descending down the hierarchy until you find the machine you want. Okay, is that clear? Any questions here? So that is just an example of DNS. We'll look at some more details here. So first thing is we'll talk about these three layers. There's a global layer, administrative layer, and managerial layer. Okay. And the idea is, as you keep coming down the tree, you will see there are more and more nodes. Okay. There are a lot more domains than there are top level domains. There are a lot more organizations and machines than there are domains. Okay. So as you go down the tree will have more and more nodes at that layer. So at the bottom you have all the machines that are connected to the internet. So that layer is going to be very large, right? Much larger than the number of domains in the internet. So that's obvious. But the other thing is that's actually important here is as you go up the tree, there are fewer and fewer changes to the DNS system. But as you go down the tree, changes may be frequent. Right? Top level domains don't get added very often. Every once in a few years they may say, here are some more top level domains. But domains within a certain top level domains get registered all the time. You can just go and register your own domain. Okay, that will add to it. And then if you already have a domain, changes within that domain are even more frequent. Machines come and go, names of machine changes all the time. So the frequency of changes increases as you go down. Okay, the fan out also increases as you go down. Okay. This is an important point. It's true of any large distributed naming system. There is more dynamics at the leaves, and then there is fewer changes at the top. And this is going to have some implications when you talk about name resolution. Is that clear? Any questions here? Yes.
This only for naming the servers.
Yes, this is the domain name system. It's an example of a naming system. In this case, not just servers, it's naming any machine on the internet.
And like how many users are possible
If your machine has a real IP address, it will be part of the system. Because it will have an actual IP address. If you have a private IP address, it will not be part of the system. Private IP addresses are addresses that you cannot actually talk from the outside. They are behind a firewall and they are given a private IP. In that case, you will not be part of your DNS because you can't reach a private IP. All public IP addresses will be here. Okay, so that's what this slide shows, saying the scale of the network is varies. As you go down, the scope is smaller. You may be down to a department where you start going into the bottom, and at the top, if you're .com, .edu, those are global in scope. The number of nodes goes up as you go down the hierarchy, and then you will see some of these issues as to what are some performance implications. I'm going to come back to that in just one domain. Okay, so I just want to show some examples here before we talk about performance. So the way DNS is constructed is it's a really large distributed database. Okay. Within the database there are records. Each record gives you some information about a machine. Okay, so you may have what is called an A record. That's a very common record that simply says here is the name of the machine, this is its IP address. That's what an A record means. Okay. You may have something called an MX record, which is basically going to tell you what is the mail server for that machine. If you want to send mail to that machine, it has to go to some other mail server. You have an MX record. You may have an alias record, which is called a CNAME record. Machines can have multiple names. They may have one IP address, but multiple names. You can construct aliases. Okay, that will be a CNAME record. Okay, and there are some other ones which I'll show you as well. NS record is the domain name server for that domain. Okay, that's the name server record. So all of this information is in your domain name system. They're all records in the database. Different record lie in different levels of the hierarchy. So you're going to keep doing these lookups and descend down the tree. Okay. Now you can go and try some of these things. I'm going to show you an example. So if you go to any Linux-like machine, and or Mac for that matter, and if you just say, you can do either ns lookup or you can just use the host command, and you can just specify a name. If you just say csu mass edu, it's going to give you, so saying this has IP address, so that's an A record. Okay, that says that machine name has that IP address. You will see that it also says that for that machine, mail is handled by, and it gives you mail server. That is an MX record for that machine. So if you send mail to that machine, it will actually be handled by that other server instead. Okay. So that's just an example of an A record. Okay. If you actually want to see more details, you can specify the verbose option, and you will see a lot more information pointed out. So you'll see it will say there is an MX record and there is an A record, and then we'll talk about mail servers that responded to your query and all this kind of extra information. And which server is telling me this information? What kind of record is it? All that you can see. Okay, so you'll see that here, this is the domain, that is unix1.cs.umass.edu is actually the naming server. That's the DNS server for that domain. We'll show you additional name servers and so on. Okay. So you can also, if you actually look at just as an example, I'm going to show you a couple more examples. So if you actually go and do this, you will see it will say that machine is an alias, and it will give you some other machine name, and then it will give you the IP address for that machine. Okay, so this is an example of a CNAME record where that machine has two names. Okay, so if you specify the alias, it will tell you that it's not a real name, it's an alias for some other name. Yes, question?
This information is being fetched from the domain names.
Yes, when you do host, it's actually sending a request to the DNS explicitly. This command is doing nothing but querying the domain name system. And these queries happen automatically. If you go to a browser and type a name, your browser is going to internally do this and then set up a connection to that IP address. Yeah, for that matter, any network communication, if you give a name, it will do a lookup for you internally. Okay. Any other questions here about the DNS? So there are a few other interesting things that the DNS will do, and I'm going to show you a couple of examples what you can use. So these are simple lookups, but in some cases you can use DNS to do additional other interesting optimizations. I'm going to show you one. Yeah, so let's just say I do host www.cnn.com. So here you will see that you basically gives you a bunch of other things, but in the end it gives you two IP addresses, okay, not one. So what that is showing is that basically either of those two machines will answer to www.cs.cnn.com. Okay, that's also saying that's a replicated web server, where when you say what is the IP address, you will get a bunch of responses saying here are all the machines that are going to answer to this IP address, and the browser can pick one. Okay. So this is going to allow you to do automatic load balancing. Okay, here is another one. So you will basically get these two IP addresses. Okay. So your browser can then perform load balancing because it can pick either one. Okay? Sometimes the order in which this is returned will keep getting scrambled. So if you just pick the top one, some browser will connect to the first IP address, some browser will connect to the second IP address, and all the requests that you are seeing for this website are getting distributed across a set of machines that are all answering to the same name. So I showed you an alias where one machine has two names. This is the reverse where one name, multiple machines share the same name. Okay, so you will return all of those resolved IPs, and then you can pick one based on whatever you are doing. Okay, clear? So this is an example of replicated servers that you can actually use DNS to do automatic load balancing if you want. Okay, that's another interesting thing. I'm going to show you one more and then we will move on. So if you actually look at, you go and resolve, let's say something like intel.com, assuming it works. So it will say intel.com is an alias for something, that's an alias for something else, that's an alias for yet another something else, and then finally it maps to these two IP addresses. Okay, that says 192.192.189.138.182. Okay. So now if you actually go and look at where that IP address resides, you will see that it is not where you expect it to be. Okay, so I'm going to show you, assuming this works. So I'm going to just say .1, and you will see that, so that subnet, which is 192.188.138.1, is actually pointing to a umass.edu machine. So if you actually try to go to the website that's at www.intel.com, you are actually accessing a machine that is inside UMass. Okay. So what has actually happened here is the domain name system is being used to transparently point you to a cache which holds the data for that website. Okay? And it is intelligent enough to send you to the closest cache based on where you are making the request from. So it figured that the request came from UMass. It said there's already a cache at UMass which holds that content, and it sent you there. If you go to some other place, you go home and you do the same resolution, it will point you to some other cache which may be somewhere else. So in some cases you may think that you are going to some far off server, but the server is actually cached somewhere else. Okay, so you actually use DNS to implement caching as well. Okay, so if you go to this website, you'll see that the performance is very fast because all the data is coming from a machine that may be in the next building. Okay, it's cached all of the data for you. Okay. So this is used by content distribution systems which are caching web content. Okay, so you will see that that's a alias for this company, this domain called akamai.net, which operates a large content distribution network. That's a web caching service that is being used by these websites to deliver content to you with very low latency. Okay, so you will not see long latencies to go to far off server. Because all this is intelligence is now built into the DNS to do this kind of optimization. So it's actually looking at where you came from, it's resolving things and so on. Okay, so I'm going to go back to this slide and talk a little bit about resolution. So having said all that, we still need to figure out how resolution is actually going to work. There are two approaches. There's an iterative resolution and a recursive resolution. So iterative resolution is as follows. You want to resolve a name. You can specify host command or a browser sends a name. It goes to the local DNS. And the local DNS is going to start at the top. So in this case, we want to resolve ftp.cs.vu.nl. Okay, that's the FTP server in the computer science department of that university in Netherlands. This is the author's computer science department's FTP server. So if you do this, you'll start at the top. You'll say, you ask the root server, what's the server for Netherlands? So you start it at the top. You'll say, what's the server for Netherlands? The root server will say, here's the machine that can tell you everything about Netherlands. So then you go to the next level server, which is the NL node, saying, where is this server that will handle requests for this university VU? Okay, and then that will do a resolution and send you back a reply and saying that's VU. We'll go to the view name server saying where is CS, and that will basically descend one more level. You go to CS, then you'll ask CS where is the machine called FTP. Okay? And then that will give you the right record, which will be an A record, which has the IP address or whatever. So this is iterative. At each point, you're basically talking to the right name servers and so on. Okay, and then all of these entries will be cached by your resolver. So the next time you want to resolve it, you may actually look in the cache and answer. Okay? Or instead of FTP, you say www.cs.vu.nl. If you have all the entries cached, you don't have to start at the top because you already know the CS server. You can directly use the cached entry and go. Okay? So caching can help you reduce the load on the servers because now you don't send every request to the server, you cache some entries. And also it improves performance. Okay. Now this is where what I was talking about, frequency of changes come in. So you can ask, how long should I cache this data in my DNS? Some other DNS server has given me a response. I have a cache in my DNS. How long should I cache it? The answer is going to depend on what level of the hierarchy did you get that responses from. Okay? The NL name server, unlikely to change frequently. It's a top level server. Okay? So you can cache it for days. Lower in the hierarchy, things change more quickly. So you don't want to keep it around for a month. If they actually change the machine, swap it out for a different machine or change its IP address, you have an incorrect response cached. So the amount of time for which you cache data will depend on which level of the hierarchy it came from. The lower level the hierarchy, the less time you are going to cache it and then you are going to throw it out. The next time if you have another request, you will restart from the top or the most recent cache data and start from there. Okay. This is iterative. Here is the other one when I stop. This is recursive. Okay, in recursive, you just start at the top and you say, you figure it out, give me the final answer. I'm not going to keep on contacting lots of servers. So you are going to inject the request at the root name server. Root name server will look at the request, forward it to the next server. The next server will send it to the next one, next, and so on. The responses will trickle up and you will get back a reply. Okay. This is referred to as recursive name resolution. Now, as you can imagine, in this case, all requests are handled by the naming system. Okay. So the top level node is going to be heavily loaded because every single request starts there and ends there. Okay, so that node better be very powerful. If you have everybody on the internet is making lookups and it goes to this one server that sits at the top, it's going to be heavily loaded. Okay. So if you have a recursive name resolution, your load is going at the top is going to be very high. But however, you may actually get lower latency because what may happen in this case is if the servers are, let's say in this case, they are on a different continent, you're continuously making cross-continental hops. Every request is traversing to a different continent, a reply comes. So that's going to be much longer round trip times. In this case, you send the request once and then it stays on the continent and sort of trickling to machines that are close to one another, geographically close to one another. So you may see lower overall resolution latency if the nodes are separated by large distances. The downside is the burden on servers higher up in the hierarchy tends to be extremely high because everything that is in their subtree goes through those nodes. Okay, so those are all trade-offs to consider, which is also shown in this picture here, which says if you did iterative, you will basically do this long round trip times. If you do recursive, you have one long hop and then several smaller hops within these servers that are close to one another. So that's going to be a trade-off. Do you want to worry about performance? Do you want to worry about load? And this is why caching helps. Okay, you typically don't want to do recursive and overburden your server. But if you cache results from previous queries, then the next time you do something, you may avoid several of these hops and start lower down the hierarchy. It will reduce your latency even though you are still doing iterative resolution. Okay? So that's all we have for DNS. I'm going to talk about other directory services next time. We ran out of time today. So we'll continue on Monday.